All right. Hello, everyone. My name is Amir, and this is a joint work with my students, Milad and Ali Reza, who unfortunately couldn't be here for visa complications, so I'm getting the honor of presenting the paper. All right, so Tor provides anonymity by using a type of encryption which is known as onion encryption. So if you communicate through Tor, you build a circuit, and different segments or flows of your connection will be encrypted using different keys. And therefore, if an adversary is watching your connection at different points, they won't be able to match the different segments of your connection by just looking at the content of traffic, because the content on different segments is encrypted with different keys, and the content doesn't match, right? However, what the adversary can do is she can try to match the timing and sizes of packets, because Tor is supposed to is designed to run as a low latency system, and therefore features like timing and the volume of traffic that is being observed on different segments is not changed significantly for the connections. All right, so this is what we call the Tor flow correlation attack. And again, the idea is that some adversary is intercepting Tor connections, and let's call them Tor flows, at different vantage points. And then the adversary is trying to match them by comparing the timing and volume of traffic being sent at different intervals. All right, so this is flow correlation attack. And different types of adversary could run this flow correlation attack. Could imagine that if an adversary is compromising a number of Tor relays, they could try to kind of collect flows on different compromised relays and try to match their patterns. Or if you are running or have access to a big autonomous system or internet access exchange point, you probably are intercepting a big fraction or a large fraction of Tor connections, and that's also give you a possibility of performing flow correlation. And there's been other kind of papers showing that even a DNS server could launch a flow correlation attack. All right, so different people could run this flow correlation attack. I'd like to claim that flow correlation is a key technique used in many attacks that have been studied on Tor. All right, so let's look at some of these attacks. Perhaps one of the key reasons Tor has adopted the idea of guard relays is to reduce the chances of an adversary in performing a flow correlation, right? So you say that some of the relays, that your first relay should be from a small set of trusted relays to make sure that hopefully these are not the adversaries. There's been different different kinds of attack that work by pushing a target user to build circuits through these compromised circuits. So for instance, if you're making a connection through a connection that the adversary only has is visibility on one end of the connection, the malicious relay will do a denial of service and push you to go through some circuit that contains the two ends. The two ends are controlled by the adversary. And there's been different studies on how an autonomous system or internet exchange point could perform flow correlation at larger scale. Recent study, for instance, shows that some of the autonomous systems have a great deal of visibility on Tor traffic. A single AS could observe something like 40% of all Tor traffic, and therefore putting them in a perfect position of performing flow correlation. And followed by that, there's been a lot of work on designing AS or path selection mechanisms for Tor that would reduce the likelihood of these malicious adversaries of performing flow correlation attack on Tor. All right. Okay, so I guess the point I'm trying to make is that flow correlation is not just some attack on Tor, is one of the most important attacks on Tor, right? And it's been extensively studied in different forms in different papers. However, it seems like Tor has not deployed efficient or effective mechanisms to defeat flow correlation attacks, except for sending packets in cells and such, which doesn't seem to work in preventing flow correlation attack. And historically, this is for two reasons. The first reason is that in Tor, the threat model does not consider resistance to a passive to a global adversary who's intercepting and watching a lot of the Tor connections. And however, some of the past papers I just mentioned show that in fact some of the autonomous systems can perform this, can be the passive global adversary, and it's not really hard in today's internet to be that passive global adversary. The second reason, which is more relevant to the talk that I'm presenting today, is that existing algorithms designed for performing flow correlation, when it comes to Tor, they suffer from offering a good accuracy, right? So you see them, they could be used in different applications, but when you apply them on Tor, the accuracy they provide in correlating flows is not really good. And you either have to give them a long observation from each flow for them to be able to give some meaningful correlation to you, or they only work on very small set anonymity set. So if you're only going to correlate flows out of 50 or 100 flows, maybe they work. All right. So existing flow correlation systems suck at correlating Tor connections. And perhaps the main reason for this is that Tor is very noisy. There's different forms of congestion and noise in Tor. And previous existing flow correlation algorithms, it appears that they haven't been able to capture this complex nonlinear nature of noise in Tor, right? And that's presumably because most of the existing designs of flow correlation systems, they either rely on making approximate and inaccurate models for how noise or latency is in Tor, and based on that, they design some algorithms. And also, many of the systems just use generic statistical correlation algorithms that, as they appear, they're not working pretty well for the case of Tor. All right. Okay, and now let's talk about what we're doing in this work. In this paper, our goal is to show that despite the fact that existing flow correlation systems don't offer good performance on Tor, we want to show that in fact it's possible with the new advances in learning to design a flow correlation system that offers accuracies much higher than what is provided by previous work. And to show this, we designed a system called DeepCorr. DeepCorr uses deep learning, as the name suggests, to learn a correlation function for Tor. And then we hope that deep learning, because it's known to kind of be good at learning complex nonlinear behaviors, we hope that using deep learning would help us to design a better correlation function for Tor. So that's why we're using deep learning. And then so DeepCorr learns a correlation function for Tor, and this is as opposed to using generic statistical correlation functions or making unrealistic assumptions about what the noise model is in Tor, right? So we don't try to model noise in Tor. We just say, let's learn how the Tor noise is in practice, and let's try to build a function for that. All right, so this is a core idea of DeepCorr. And let's, I guess this is the architecture. I'll just give a brief overview of how it works. So suppose that you have two suspect flows, flow 1 and flow 2, and you want to see if they are correlated. And correlated means that they're probably the ingress and egress parts of the same connection. So at the left side, we see that, I guess it's not so visible, but what we're doing is that we kind of pair the features of two flows that are supposed to be correlated for correlated flows together. So like, for instance, here we see that the IPDs, the interpacket delays and sizes of packets on different sides and at different points of the two flows are being paired as the inputs to the model. Then we have a 2 layers convolutional neural network, which we're hoping it's going to capture the high level features of noise in Tor. And then eventually we use a fully connected network to combine all these features into a single metric. And that single metric is what we use for deciding whether flow 1 and flow 2 are correlated. Okay, so that's a normalized metric between 0 and 1. 1 says it's very likely to be correlated, and 0 says that they're very likely to be non-correlated. And yeah, so we train this model. So we collect a large number of correlated and non-correlated flow pairs on Tor, and then feed them for the learning. And we use the Atom optimizer for converging the model. All right. Okay, so let's look at some of the results, and you can find more details on the architecture. Perhaps it's not the most important thing, but let's talk about the results. So first of all, let me explain how we did how we collected the flows for experiments. We browsed, so we collected correlated flow pairs by browsing the top 50,000 Alexa websites. And we enforced these connections to go over 1,000 different circuits. So we made sure that these are distributed over 1,000 different Tor circuits. And then we collected these flows in a span of 6 weeks. First, we collected in a 2 weeks period, and then we paused for 3 months to evaluate the impact of time over training, which I'll talk about. And then after that, we collected for another 4 weeks. And the data set we've made it available online. So if you want to kind of use it for some reason, for some experiments, you can do. All right, so let's look at some of the results. Perhaps this is the most exciting results to share. So in this figure, what you're seeing is the false positive and true positive compared with DeepCorr and a number of algorithms that have been used in previous full correlation studies. And all of the algorithms are using the same setting. For all of them, we're using 300 packets from each flow. So like we're correlating flows by only looking at the first 300 packets. And as you can see, there's a wide gap between the performance of, or a huge gap between the performance of DeepCorr and existing flow correlation systems, right? So, and what this tells us is that now for the first time, a flow correlation algorithm is able to work with such a short links of traffic, right? So like previous, for the other algorithms, of course, a few links of the observation for each of the flows, they start to produce better results and provide better accuracies. But like when we reduce when we only capture as short as 300 packets, we see that DeepCorr is the only one who's able to perform a reliable flow correlation, right? And it tells us that now it just makes the job of flow correlation adversaries much easier, because now they can achieve very good accuracies in flow correlation by just observing much smaller lengths of flows, right? Okay, so like I said, during the training, we collect a lot of, we make a lot of connections. We force them to go through over different circuits. And the reason we feed them through different circuits and to different destinations is that our goal is to learn a correlation function which is independent of the circuits that has been trained on, right? So we want to correlate something that once you test it on a flow, even if the flow is going through a different circuit, but because the model has somehow captured the high-level idea of noise in Tor, it's still able to perform well, right? And from this figure, it shows that, in fact, the model is working well. So the blue lines shows when you're training on a set of flows and then testing on a set of flows that use the same circuits as the flows used for training. And the red line is the case that you train on some flows over some circuits, and then you test it on flows that are on exclusively different circuits, right? And you see that the results are statistically similar, which is good news for the system. All right, so I guess one important question would be, if you design any learning system, how often you have to retrain the system. So this graph shows the correlation metric over time, and as you see that, so we use a model that we trained on day 0, and then we test on flows that we have connections that we have made on different days. And you see this, we have done it for 30 days. And you see that at some point, the performance of the algorithm starts going down. So maybe around 3 weeks or close to a month, it's the time that we have to retrain the model again, right? But the good news is it's not as frequent. We don't need to retrain as frequent as like a day or a week or something, right? So maybe once a month is enough for the adversary to retrain the model. So like any other flow correlation schemes, you can imagine that longer flow observations should improve the performance of the model. So we see that by increasing, so the lowest line is when we only use 100 packets from each flow, and the top line is when we use 450 packets. You see that there's a big jump when we increase the length of observation. And what this suggests to us is that the flow correlation adversary could perhaps implement the attack in a hierarchical manner, in a way that maybe you apply the attack on using, let's say, 200 packets of all the connections, and then you narrow down the suspect correlated flows. Now you keep collecting more packets, and you then perform the more expensive, more time-consuming like attack with 400 packets or 600 packets and those things, right? So this suggests us that if we implement the attack in that way, it's likely to even improve the performance. Help us to run it at larger scale. Another thing, as you would expect, increasing the size. So in most of the experiments, we have trained a model with 5,000 pairs of correlated flows and similar number of uncorrelated pairs. And you see that by increasing the number of the size of the training set, you can improve again the performance, right? So in that case, we were only able to do it with 5,000 flows, but you can imagine a resourceful adversary will probably be able to do much better and further improve the performance. And finally, when we compare, I guess the question would be, okay, deep learning, the algorithm, perhaps compared to cosine similarity, it probably takes more time, which is true. So if you compare the time to perform a single correlation with DeepCorr, it's 2 to 4 times of that with previous full correlation algorithms. But then that's when they use the same lengths of flow, in which case our system offers a much better performance. But then when you compare to those algorithms offering the same accuracy, then in fact our algorithm would be much faster. So like in this case, for instance, if you want to achieve the same accuracy with Raptor, then you have to over much longer lengths of flows. In that case, the time to compute a single operation would be 20 milliseconds compared to DeepCorr's 2 milliseconds. All right, so let's talk about countermeasures, right? This seems to be serious. So one avenue for defeating these kind of flow correlation attacks is to minimize an adversary's chances of intercepting a long number of Tor connections. And this is orthogonal Tor work. And like I said at the beginning of the talk, there's been a lot of work designing AS-over path selection mechanisms to make sure they reduce the chances of an adversary intercepting connections. But the countermeasure which is relevant to this work is obfuscating traffic features. So we evaluated the attack on some of the Tor's pluggable transports. And so nowadays, it's, I guess, these mechanisms are only deployed by bridges, and even the guard nodes, if they're not like acting as a bridge, they don't deploy any of these, right? So these are not deployed, but assuming that the Tor relays would deploy some of these pluggable transports, we see that using some of these would impact the accuracy of the attack. And in particular, OPS4 with the IAT mode, it seems to have a good impact on the accuracy of the attack. I have to mention that for this experiment, we have collected a much smaller set of flows for ethical reasons that I can explain, but so you shouldn't compare the numbers to the number I had previously, but at least it shows that some of the pluggable transports work better than the others. However, the challenge is using such defenses in the wild by Tor and deploying them at larger scale, let's say in all the relays. It doesn't seem to be the most feasible solution because each of these countermeasures that have their own overhead and kind of utility problems with Tor, right? So therefore, we believe that an interesting avenue for future work is designing efficient countermeasures that would reduce the chances of low correlation, but at the same time preserve the utility of connections in Tor. All right, so let me conclude. I hope we have shown that flow correlation is not just a hypothetical attack that someone maybe could deploy. We believe that with advances in learning, with the increased resources of adversaries, this is something feasible. And we hope that the research community looks at the problem of designing efficient countermeasures to this problem. The code in this dataset is available at this URL, which is also linked in the paper. All right, thank you so much.
Thanks for your talk. So didn't you say at the beginning you had, like, your data set was 25,000 connections?
Right.
But your test is pairwise, right? So you have to take an entry and an exit, and it gives you a bit. Well, it gives you a value between 0 and 1.
Right.
Take another entry, another exit gives you a bit. So you have 25,000 of them, then you have 600 million of these pairs you have to test. And so I have two issues. One, if it's taking 2 milliseconds per, that's a lot of milliseconds. But more to the point, your false positive rate seemed to be like 10 to the minus 3.
Right. So so
huge for that.
Right. So the 25,000 pairs, we didn't use them in all experiments. So the 25,000 pairs is the total number of flows we use across all the experiments. For most of the experiments, we mostly used 2,000 to 5,000 pairs of those flows for training.
What do you think a realistic number for an adversary who's capturing traffic?
It would be much bigger, but like I said, the attack could be implemented in a hierarchical way. So you could say, let me do the attack with only maybe 100 packets from all the flows, and then I get a smaller set, and now I keep collecting more packets for those flows, and we keep going, right? So, but that's true. If you want to do this in real world, the adversary is possibly intercepting many more flows, and there's also other mechanisms for kind of pre-filtering some of those connections. So you can look at the start time and end time of if there's a big mismatch, those you can probably rule out.
Thanks for the talk. I have two questions. One quick one. You said you use size as a feature in your packets. I mean, Tor breaks things up into cells. Why don't you just look at the timing of the cells?
So still, at the IP level, the cells are concatenated, and some packets, do
you think that's relevant, or do you think looking at it at the cell level would actually get better results? Like
few cells at the exit that you see between the exit node and the...
Oh, I see. You don't see the cell level there. No, that's a good point. My other question is, what do you think changes over this month to make your accuracy go down? Because I mean, it sounds like you're inferring some features about how flows, the noise that Tor network introduces, and they're global features, like you say. They're not dependent on the path. Right. So do you have any sense for why it gets worse over time?
Yeah, I guess that's a good question. We've been thinking about it. We don't have a definitive answer, and I guess I'd like to hear some thoughts on it. It could be, I guess our guess is it could be changes in dynamics of like overall maybe throughput or capacity in Tor, maybe if there's a new release or something, maybe the capacity of the whole network changes, and maybe that impacts the overall nature of noise in Tor.
Did your accuracy really go down?
Yeah, so I guess a little bit. Yeah, it's not much.
If those are error bars, you're not saying anything about your accuracy.
No, yeah. So the average, you see that the average is going
Yeah,
down.
but the error bars are this big.
Yeah. All right. Yeah, but
the accuracy may have well gone up and be consistent.
yeah, exactly. No, so but the overall accuracy, right? So yeah, so for some of the samples, yeah, we see some big variation, right? But it's still, if you look at the trend, you see that it's going down. Well, all right. So I have a figure. I don't think I have it in. So this is showing only over a month. We have a figure in the paper comparing with a 3 months gap, and there you see that it's definitely a big difference, right? I don't think I have it in my slides, but one of the figures you can see that with a 3 months gap, in fact, you see that it doesn't even work anymore, right?
I mean, I guess if the point is you only need to retrain once a month, then. Right.
Or maybe
point
more.
made, right?
Yeah.
So can you go back one slide to 16? So in this situation, you are saying you trained on a circuit and then you're comparing it with...
We train on some circuits and test on, so like for the training, it's not on a single circuit.
Yeah.
Yeah.
Okay,
so the samples used in the training are, let's say, from 500 circuits, and for testing, we use circuits from connections over other, again, the blue line, the same circuits, the red line, different circuits.
Okay, so this is basically a version. I guess I'm confused. Is this a version of what you have on the following slide, which says that 1 week later things aren't so different?
No, so this is, we want to show that the results don't, we want to show that the model that we have trained, it's not overfitting to the exact, to the circuits that we use during the training. So we want to show that the adversary doesn't have to collect traffic over all the circuits for training, right? Even a good number of circuits, you train on these. And if during a test you get a flow that is over a different circuit, still it works. It doesn't, you don't need to have trained over the same circuit that you see for, like, that is for the flow that you're testing on.
Okay.
Can we take the rest of the discussion?
Oh, come on.
I'm sorry. We're already 4 minutes over.
All right.